So, if you've ever dipped your toes into the Zephyr real-time operating system, you know it is incredibly powerful. But then you get to its Bluetooth stack, and, well, things can get complicated fast. It's one of those features that gets developers really excited, but man, at first glance, it can be a little overwhelming. I mean, just look at this. This is only some of the Bluetooth samples that come with Zephyr. You've got your basic stuff like beacons and peripherals, but then it goes all the way up to complex mesh networks, audio streaming, direction finding. The list just goes on and on. You'd think you need to be a rocket scientist just to get a light to blink. But what if I told you that this entire massive universe of features is all built on one single, really elegant idea? That's what we're going to break down. Right, because underneath all that seeming complexity, there's a really smart architecture. And once you get that one core principle, everything else just kind of clicks into place. So let's pull back the curtain and see what makes this whole thing tick. And here it is. This is the single most important thing you need to understand about Bluetooth, not just in Zephyr, but in the official spec itself. Everything, and I mean everything, is split into two distinct parts, the host and the controller. You can think of it as the brains of the operation versus the muscle. Okay, so what do these two layers actually do? Let's take a quick look at their jobs, because understanding this separation is really the key that unlocks all the flexibility and power of Zephyr's Bluetooth stack. So the host is the big picture thinker. It lives just underneath your application code, and it handles all the stuff that doesn't need to happen in a split second. This is where your app's logic is, where security is handled, and where all the data is organized before it gets sent. Basically, the host decides what to say. The controller, on the other hand, is the muscle. It's a pure real-time system that is all about timing. Its only job is to manage the radio, scheduling packets, listening for stuff coming in, and just handling the raw communication over the air. It doesn't know or care what the data means. It just knows how to send it and receive it, period. Now, because of this clean separation, we get some amazing flexibility. You can run both the host and the controller on a single chip, a system on chip, where they just talk to each other inside the chip's memory. Or, and this is where things get really interesting, you can put them on two totally separate chips. They're just connected by a simple interface like a UART. This dual chip setup is a total game changer. Okay, so that's the architecture. But what about the actual data? Bluetooth is full of jargon, right? GAT, services, characteristics, it's a lot. To make it all make sense, let's use a super simple analogy, a restaurant. So first up, your Zephyr device, the thing with the sensor on it, maybe a heart rate monitor, that's the server. It is the restaurant. It's got all the data, all the goods, just waiting for someone to ask for it. Now, your phone or your computer, that's the client. It's the customer that just walked into the restaurant. It doesn't have the data, but it knows it wants to get it from the server. So how does the customer know what's available? How do they know what to order? Simple. They look at the menu. In the world of Bluetooth, that menu is called GAT, the Generic Attribute Profile. It's the standard format that the server uses to list out every single piece of data it's willing to share. You know how a good menu is organized, right? You've got sections for appetizers, main courses, desserts. In GAT, these sections are called services. So a heart rate service, for example, just groups all the heart rate related data together in one place. Makes sense, right? And finally, inside each of those sections, you have the actual items you can order. Fries, Coke, a salad. In GAT, these are called characteristics. The heart rate measurement characteristic is the actual number, the specific data point that the client, the customer, actually wants to get. All right, so now we get the architecture and we get the data structure. Let's put it all together and see how this actually solves a really common and powerful real-world engineering problem. This is where the theory gets really practical. So imagine this scenario. You've got a fantastic, powerful cellular IoT chip, something like Nordic's NRF 9160. It's amazing for connecting to the cloud from anywhere, but it's missing one key feature. It has no Bluetooth radio. So what do? How do you add that capability? You guessed it. This is where that host/controller split becomes your superpower. You use that dual chip setup. The big NRF 9160 runs your main application, and the Bluetooth host, the brains. Then you connect it to a smaller, much cheaper chip, like an NRF 52, and its only job is to run the Bluetooth controller, the muscle. They communicate over a standard language called the Host Controller Interface, or HCI. And the beautiful thing is, Zephyr makes this pretty straightforward. You're not starting from scratch. You just flash that little NRF 52 with a ready-to-go controller image from Zephyr. You write your main app on the NRF9160 like you normally would, connect a couple of wires between them, and when it boots up, the big chip just pokes the little one to make sure they're in sync. It's a really elegant solution. So, after all that, what's the big payoff? Why would you go through the trouble of connecting two chips like this? Well, the result is what makes this architecture so incredibly powerful for real-world products. Here's the magic trick. For you, the person writing the code, all of this complexity is completely invisible. As Jared from Circuit Dojo puts it, you literally just use the Bluetooth commands on your main chip as if it had a Bluetooth radio built right in. Zephyr handles all the background communication to the other chip for you. It just works. And the benefits are not just in the software. By using a special low-power communication method between the chips, the power draw for this whole Bluetooth connection can be absurdly low. We're talking around 30 microamps. 30! A normal connection would be drawing 1 or 2 milliamps. That's nearly a 50 times improvement, which is the difference between a battery lasting for weeks versus lasting for years. So, at the end of the day, what you have isn't a compromise at all. It's the absolute best of both worlds. You've got the long-range power of a cellular connection, and you've got the short-range, ultra-low-power convenience of Bluetooth for things like device setup or pulling sensor data, and it's all controlled from one single application on your main processor. And this really leaves us with a final, very cool thought. This architecture proves you can essentially bolt on brand new hardware features to a chip that was never designed for them. It completely changes how you can think about designing products. So the real question to ask yourself is this. Once you realize that pretty much any processor can be taught to speak Bluetooth, what are you going to build?